Hey Dr. Pinchbeck, it's Zach here. You wanted me to solve question 23, so that's what I'm going to do in this video. So the circumstances we get are that the derivative function dy over dt equals 2y plus 1. And we have to solve for y of t when y of 0 equals 3. Okay, so I've written out this problem so I can write the steps down. So the first part, the harder part, is to find a general solution to the derivative equation before we get to the easy part and find a specific solution that matches this circumstance. So we have to talk about separation of variables, and that is when you separate variables so like terms of variables are together. So the y terms are not together and there's just one t term. So what we have to do is divide 2y plus 1 on both sides and then multiply by dt. So that leaves us with dy over 2y plus 1 equals dt. Next, what we have to do is take the integrals of each term. So the easy one is the integral of dt. So we can write here that the integral of dt is simply t plus c. That's the general term for that, because it's a constant and the derivative of the constant is 0. That's the general solution for integral dt. The harder one is the integral of dy over 2y plus 1. So to solve that, we're going to use a little technique called U-Substitution, which means we're going to rewrite this value in terms of u du. Okay? So we'd have to determine what our u will be, and thereby also what du will be. So we can establish that u in this case will equal 2y plus 1, and du will equal the derivative of 2y plus 1, and that is simply 2. So we can say that du over u equals 2y plus 1. But the problem is, when we have this in terms of y, there is no 2 on the top. There's a coefficient of 1, not 2. So we just have by half. And as a result, we can say that dy over 2y plus 1, the integral, equals the integral of 1/2 times du over u. And one rule about integrals is, with a coefficient, you can move that out in front of the integral. So that would be 1/2 times du over u. So what we have to know now is what the antiderivative of 1 over u is. Well, you might note that the antiderivative of any term, let's just call this t, is equal to the natural log of the absolute value of t plus a constant term as a general solution. So we can state that the integral of du over u equals the natural log of the absolute value of u plus c. And since we have a 1/2 out front, we can say that the integral in terms of u equals 1/2 the natural log of the absolute value of u plus c. So all we have to do is substitute 2y plus 1 for u, and we get 1/2 natural log of 2y plus 1 plus c. So we can confidently rewrite this integral as equaling 1/2 times the natural log of 2y plus 1. So now we can state that 1/2 natural log of 2y plus 1 equals t plus c. Next, all we have to do to get rid of the coefficient of 1/2 is multiply on both sides. So we multiply by 2, so the natural log of 2y plus 1 equals 2t, and since 2 times c is still give us a coefficient, we can just say that's 2t plus c. And now to get rid of the natural log, we set everything as an exponent with a base of e. So e to the power of a natural log of a term is what that term is. So 2y plus 1 equals e to the power of 2t plus c. And since we have e to the power c, and that is c, which is a coefficient, we can state that it equals c times e to the power of 2t. Next we subtract 1 on both sides, so we get 2y equals c e to the power of 2t minus 1, and all we have to do is divide by 2 on both sides. So 2 divided by a constant is still a constant, so we can say that y is equal to c e to the power of 2t minus 1/2. So that is a general solution. But let's see if that actually fits the derivative. So now we're going to take this in two different ways. We're first going to take the derivative of the y function first, and then we're going to also plug in this function for y and see if they equal each other. If they do, this means that this works for a general function. So the derivative of c e power of 2t minus 1/2. So, with the chain rule, we can say that the derivative is c e 2t times the derivative of 2t. So that would equal 2. So we have 2c e to the power of 2t, and the derivative of negative 1/2 is 0. So that's our derivative for the function. Now let's plug this function into 2y plus 1. So 2 times ce to the power of 2t minus 1/2 plus 1. So 2 times ce to the power of 2t is 2 ce power of 2t. And 2 times negative 1/2 is negative 1. And then add plus 1, and this just equals 0, so we can cancel those out. And And we can see here that our two results are exactly the same. So this is a general solution for the derivative. Now, that was the hard part. Let's get to the easy part. Now that we have a general solution, let's go to the specific solution. So it says that y of time t equals 0 equals 3. So we have a t value and we have a y value. We can just substitute 3 for our y value and 0 for our t value. So 3 equals c e to the power of 2 times 0 all minus 1/2. Now, interestingly, 2 times 0 gives us 0, and e does not equal 0. You can remember that the rule that any base that does not equal 0 raised to the power of 0 equals 1. And 1 times c gives us c. So we can simplify this to say that c minus 1/2 equals 3. And we're almost done. So we can do some simple addition with this. We add 1/2 on both sides. So 3 plus 1/2, of course, equals 3.5. But in terms of neatness, because we're working with a coefficient, in terms of neatness, I'll rewrite this as an improper fraction of 7/2. So now we know what our coefficient is for the general solution, and we can apply it to the specific solution, and therefore we can include that our specific solution is y of t equals 7/2 e to the power of 2t minus 1/2. So that is our solution to the question.